Standard methods for rigid body simulations leave a lot to be desired in terms of the secondary dynamics that are exhibited during impacts. Although the box in this scenario comes crashing down and collides with a table, we are unable to discern important physical properties about the box, such as its mass or the magnitude of the impact. And quite simply, the simulation looks boring. We present distant collision response, which is a method for approximating the vibration response due to collisions in rigid body simulations by using a pre-computed reduced elastic model. To render this process more efficient, we compute the response using a digital IR filter. The response is computed as a displacement at FEM nodes that is then rendered as an impulse at existing contacts. This causes disturbances to objects already resting on the surface of DCR bodies. Our approach is efficient and is suitable for real-time applications, and as you can see, it really livens up rigid body simulations. The first step in our approach is to detect new collisions in the rigid body simulation that result in an impact. Then, these impact collisions are mapped to an FEM mesh that corresponds to the collision proxy used in the rigid body simulation. We then use a pre-computed FEM model to map collision impulses to a reduced set of elastic modes. A collision response at distant contact points is then computed based on a displacement due to the force loading obtained from the rigid body constraint solver, which ultimately results in a disturbance at distant collision bodies. Here we see distant collision response in action. A heavy pot is dropped onto a table, causing plates and cups to jump. The collision response of the table is computed using a reduced FEM model using the first 20 modes. Observe that even stacked objects exhibit plausible secondary dynamics. By comparing to an FEM simulation with a small time step, we see that distant collision response gives dynamical behavior that is qualitatively similar to the ground truth. In this example, the impact of the truck hitting the base of the cliff causes the rocks perched above to come tumbling down. For larger objects, such as terrain, we propose an approximate spatial attenuation model where vibrations propagate as traveling elastic waves. We compute a scaling of the initial amplitude due to impact. Material absorption and attenuation due to geometry are both considered. Furthermore, since we are mainly interested in the effect of traveling waves observed at distant locations on the surface, we use a geodesic distance between points to compute the distance from the source. At runtime, the geodesic distance is cached. Applying the spatial attenuation model to the scaffold example, the approach plausibly simulates the response to the toolbox falling on the scaffold. The constant c is tuned for each specific object, but by modifying the exponent term beta, we can control the localization of the response. Thanks for watching. Please see our project page for the paper and more examples of distant collision response.